Good afternoon, and welcome to GWPC's ASR MAR work group webinar on PFAS transport in the Vadose zone, implications for managed aquifer recharge. This webinar will be recorded and slides will be available later. Today's presenter is Dr. Marc Brousseau. Before we get started, just a few announcements about the work group. We were formed in 2019, and we serve as a forum for state, tribal, federal, and local governments and organizations to communicate and collaborate on efforts around ASR and MAR issues and topics. This was part of US EPA's National Water Reuse Action Plan, and we work as a leader to increase understanding of current aquifer storage and recovery practices. For more information, you can find us on www.gwpc.org. On that website, you can find, if you go to the ASR and MAR work group, you'll be able to find more information and past webinar slides and recordings. And during this webinar, all audience members will be muted. As a tip, just close out all non-essential programs on your desktop, especially email, Skype, Teams, etc. Please type your questions as we go in the chat box. Please keep in mind time is limited and we may not get to every question. We will, to the extent possible, post responses after the webinar on the workgroup website. Thank you. Some announcements. Once again, under available resources at gwpc.org, you can find our ASR MAR workgroup collection of ASR MAR resources. You can, and so announcement, the GWPC annual forum is September 10th through 12th, 2024 in Nashville. It will cover a broad list of topics, including ASR, MAR, and PFAS. And we encourage people to save the date and submit an abstract if they have a topic they are interested in presenting. One perk of presenting is that you receive a healthy discounted registration to the remainder of the conference. And abstracts will be accepted until May 3rd. And so Dr. Marc Brousseau is a professor from the University of Arizona. He is a professor of hydrology and environmental chemistry. He is a fellow of the American Geophysical Union, the Geological Society of America, and the Soil Science Society of America. His research is focused on developing a fundamental understanding of the factors and processes influencing the transport and fate of contaminants in the subsurface. He is also interested in the development and evaluation of innovative subsurface characterization and remediation technologies, and the evaluation of risks posed to the human health by contamination. Recent research efforts have included focused on the transport and behavior of PFAS in the subsurface environments, and this includes experiment-based investigations of PFAS retention and transport processes, development of mathematical models and screening tools, and field-based studies of PFAS leaching and mass discharge. And Dr. Brousseau.
Thank you, Jason. I'll be sharing my screen. So I will go back in now and change it to the total view slideshow. So are we good to go?
Yes, looks great. Thank you.
Hello, everyone. It's a pleasure to be participating in this webinar today. I'd first like to acknowledge my current and prior collaborators, as well as our funding sources. As depicted in this diagram from the ITRC, there are numerous sources of PFAS released to the environment with subsequent transport to and within the atmosphere, surface water, soil, and groundwater. Today, I'm focused on PFAS at managed aquifer recharge facilities, where a potential impact of concern is leaching of PFAS from the recharge basin through the Vadose zone to groundwater. So I will start today with a case study we've conducted at the Sweetwater Recharge Facility here in Tucson. This facility is permitted to recharge treated municipal wastewater of up to 1.6 million cubic meters a year. The facility started operations in 1989. The original treatment plant operated until 2014 and conducted secondary treatment, and a new treatment plant came online in 2014 and conducts tertiary treatment. The depth to groundwater beneath the basins ranges between 42 and 48 meters below ground surface. The estimated transit times to groundwater are roughly 30 days with high variability. So this map here in the bottom right depicts the facility. If you can see my cursor, the original basins are here on the bottom left, and the newest recharge basins are here in the north section of the facility. So you can see the basins are arranged along the Santa Cruz River here. The bar chart here on the bottom left shows concentrations of different PFAS in groundwater beneath the basins. We can see that PFOS, shown here as the bluish green bar sections, are present in the highest concentrations. Second, we see that the concentrations in groundwater are higher than the concentrations currently in the wastewater treatment plant effluent, shown here on the very right-hand side bar. So looking at the different ranges of concentrations, as well as the map here on the right-hand side, we see, first of all, that the groundwater concentrations are highest for the original basins here, with the dark purple reddish colors. And so as the original basins, these receive the most wastewater from the original plant. Conversely, we see that the groundwater concentrations are lowest for the newest basin, which received wastewater only from the new wastewater treatment plant. So these figures show changes in groundwater elevation beneath the recharge basins, along with changes in the sum of PFOS and PFOA in groundwater. So looking at the two figures, we can see that there appears to be correlations between groundwater level fluctuations and changes in the PFAS concentrations. So these results indicate a possibility of leaching of PFAS that's present in the Vadose, wherein as groundwater levels rise, that captures some PFAS that has been retained in the Vadose. So to assess the impacts and evaluate potential mitigation actions, we need to understand the processes influencing PFAS retention and leaching in the Vadose. To do so, we have several critical questions to address. First, how are PFAS retained in the Vadose? What are their retention processes? Second, how long are PFAS retained in the Vadose? So what are the magnitudes of retention and what is the leaching potential? And third, what is the magnitude of mass discharge to groundwater, or the leaching rates, recharge rates? So addressing these questions has been a major focus of our research program here at the U of A. So PFAS migration in the Vadose is a function of several factors. Source type is very important, such as AFFF sites versus biosolids or wastewater application sites that mediate the types of PFAS present and the relevant concentration ranges. Of course, site conditions are very important. Soil properties, heterogeneities, presence of other contaminants, PFAS mixtures, and precipitation and evapotranspiration infiltration rates are critical. And then finally, we have transport and retention processes such as solid phase sorption and absorption at air-water interfaces, and then the impact of infiltration recharge dynamics. So this latter group of processes will be the focus of the remainder of the presentation. So to look at retention processes, we can use the simplified retention analysis approach where we focus on retardation factors. So of course we know that this approach doesn't account for non-ideal behaviors such as non-equilibrium conditions, non-linear partitioning, and so on, but it's a useful means to assess the distribution of PFAS amongst the different soil phases. So here we have the retardation factor equation with the first two terms on the right-hand side being very familiar, commonly used, where the one in blue represents PFAS or any other constituent of concern in the pore water. The center term in brown represents the mass of the constituent sorbed by the soil grains, by the solid phase. And then for PFAS, we add this additional term on the right-hand side in green, which represents the mass absorbed at the air-water interface. So we'll be looking at these different terms and how they influence PFAS retention. And so we know retention is a function of the properties of the PFAS as well as properties and conditions of the soil. In terms of PFAS properties, most PFAS are amphiphilic, meaning they have both nonpolar and polar regions and therefore behave as surfactants. So we have here PFOA depicted in the upper left diagram, where the polar head group is circled in blue and the nonpolar tail is in this red rectangle. So PFAS chains are both hydrophobic and oleophobic, which provides both water and oil repellency. So these special attributes make PFAS useful for many applications. However, they also cause transport to be complex. So a brief overview, I'm sure we all know this, but PFAS have all different types of surfactant head groups, including anionic, cationic, zwitterionic, and non-ionic. In addition, PFAS have different types of tail structures, where we have the perfluoroalkyls, where all carbons in the chain are fully fluorinated. We have straight chained and branched chain. We have longer chain, we have shorter chain, and we also have the polyfluoroalkyls, where some of the carbons in the chain are hydrogenated rather than fluorinated. So these differences in molecular structure impart differences in transport and fate behavior, which is one of the primary reasons why the transport of PFAS, particularly in the Vadose zone, is very complex. So this is the first point at which we can address questions, if there are any questions.
Yes, Mark, I have one question here. Did the city of Tucson, the operator here, identify where the PFAS originated in their sewer shed, and have those sources been eliminated?
So I will jump back. So that's a very good question. I will jump back here. So as I mentioned, from this figure, we can see that the concentrations in groundwater beneath the basins are for the most part higher than the current concentrations in the treatment plant effluent. And so based on analyses of different potential sources in the vicinity of this facility and other issues, at least our operating hypothesis, so we can't speak for Tucson Water, but our hypothesis is that the concentrations of PFAS in the treated wastewater may have been higher back in the early operation period of this facility. As I mentioned, the original treatment plant operated until 2014, starting in 1989. And we know, right, there has been the phase outs of PFOS and PFOA use. And so we hypothesize again that the concentrations may have been higher in the earlier stages of operation, and now they're much lower coming into the treatment plant because of the phase outs of their use. So that might be one primary reason. In addition, noting here that secondary treatment was used for the original treatment plant. However, they're conducting tertiary treatment with filtration for the new plant. So that also may have some impact on the concentrations coming into the recharge facility. So hopefully that addresses the question. So
we don't have any others at the moment.
Okay. So just to add on to that, I did want to mention that Arizona Department of Environmental Quality conducted an assessment of the state some years ago, and in their report, they noted that there were no known industrial or manufacturing sources of PFAS in the Tucson region. All right. Okay, moving forward, let's focus now on retention processes. So first, we will look at solid phase sorption. So sorption of PFAS by soil, sediment, and aquifer material or geomedia is quite complex compared to many of our traditional hydrophobic organic contaminants or HOCs. And the sorption is a function, of course, of PFAS molecular structure and the geochemical properties of the geomedia. So in this diagram on the bottom left shows, as we all know, that the geomedia are geochemically and physically heterogeneous. So we have the primary constituents such as silica, and then we have metal oxides, we have organic matters, we have clay minerals, we have biological components, making this a very heterogeneous system with which the contaminants such as PFAS can interact. Now moving to the bottom right-hand diagram, because of the presence of these different constituents in the soil, we can have multiple sorption mechanisms for PFAS. So our primary sorption mechanism, of course, is the hydrophobic interaction, because the PFAS tails don't want to be in the water. We also, though, can have, for example, electrostatic interactions between the head groups, the polar head groups of PFAS, and the different soil constituents. So again, this makes sorption of PFAS generally more complex than some of our traditional HOCs. To evaluate partitioning and sorption in particular, we can use QSPR analysis. So QSPR stands for Quantitative Structure Property Relationship Analysis. This is an empirical approach where we take measured data, such as measured sorption coefficients or measured aqueous solubilities, and we attempt to examine correlations between those properties and molecular descriptors, which are representative of the molecular properties of the compound of concern. So example common descriptors are the number of carbon atoms for surfactants, the number of carbon atoms in the chain, the number of fluorinated carbons, which is commonly used for PFAS, and then molar volume, which represents the volume that that molecule occupies in solution. So we can use a QSPR analysis to characterize partitioning behavior. So as we go through, hopefully we'll see what I mean by this. And so in terms of the descriptors, as I mentioned, the number of fluorinated carbons in the chain of PFAS is the commonly used approach to characterize different types of partitioning behavior, where say the log KD or the log KOC is plotted as a function of the number of fluorinated carbons. And so here I've plotted this number of fluorinated carbons along with the molar volume. And so with that dotted line, we can see that it's a one-to-one correlation, meaning the number of fluorinated carbons works well. It's very representative for the standard common PFCAs and PFSAs. but it does not work at all for these more complex PFAS, such as branched PFAS and the polys and the non-ionic, which we can see out here. And so we use in our research molar volume, which fortunately is relatively easy to determine based on the quotient of molar mass and the density. So we'll be coming back to this QSPR analysis as we go through the presentation. So here is an example of the QSPR analysis for partitioning, with specifically examining adsorption at 3 different interfaces. So here in this figure, I've plotted log K values for adsorption at the air-water interface here with the blue data symbols, adsorption at the soil-water interface represented by the red symbols, and then adsorption at granular activated carbon water interface represented by the brown triangles. And so we can see nice linear relationships between the log K and molar volume for the air-water interface, which represents the most physically and geochemically homogeneous interface of these 3 types of interfaces. And so a uniform log linear relationship is indicative that the hydrophobic interaction mechanism is mediating the driving force for partitioning. However, we can see there appears to be some deviation for adsorption at the soil-water interface, and we'll be coming back to that shortly. So in terms of quantifying PFAS sorption, we all know that the standard approach for characterizing sorption of hydrophobic organic contaminants is focusing on the KD and specifically correlating the KD to the KOC, which is the organic carbon normalized sorption coefficient, and the fraction of organic carbon. So of course, this standard approach is based on the premise that the organic carbon constituents of the soil mediate the sorption of that contaminant. And so a question is this approach representative for PFAS? So recently conducted a meta-analysis of PFAS sorption, looking at sorption of long chain versus short chain. So it compiled 11 studies from the literature where batch sorption experiments were conducted. So it's important to keep in mind these are based on batch sorption experiments. Across these 11 studies, a total of 65 different soils and freshwater sediments were used, which represents a very wide range of organic carbon contents, silt and clay contents, and pHs. It's also important to note that the data I'll be showing here is a composite of the results of these studies for 16 PFAS, 9 PFCAs, and 7 PFSAs. Right? So it does not include other types of PFAS. So in this figure, we see plotted the log KOC as a function of molar volume for these series of PFAS. The closed symbols represent the long chain and the open symbols represent the short chain as defined by the Buck et al. Work. And so we have 6 different studies here compiled together. And so we observe that the long chain fall on this solid black regression line as shown in the prior figure, this log linear relationship between the log K and molar volume. However, we see on the left here that the different short chain PFAS deviate from the relationship that represents the long chain. And so we can refer to this behavior of the short chain as enhanced sorption of the short chain PFAS, meaning they have greater sorption than what we would anticipate based on the regression that represents the long chain. So here is a second figure where I've plotted individual log KOC values for the different PFAS for individual soils with different organic carbon contents. So in the legend there, I have the different soils arranged from lowest organic carbon to the highest organic carbon content. So you can see the lowest is 0.08, and it goes up to 27 to 41% organic carbon content. So a very, very wide range in organic carbon contents. So examining the figure, we can see that it appears that the magnitude of deviation from the long chain regression line is greatest for the soils with the lowest organic carbon contents. And if we look for a moment at the red circles, which represent the data for the highest organic carbon content soils, we see that the short chain actually fall on the regression line for the long chain. So it appears that if we have very, very high organic carbon contents present, then the short chain have consistent sorption with the long chain. But the deviations are much, much greater for these soils with very low organic carbon contents. So this is indicative that the PFAS sorption for the short chain is mediated by additional soil components such as the clay minerals and metal oxides. And we can see further evidence of that here in this figure, where I've plotted two data sets, one for a soil with very high silt and clay contents and another soil with the lowest silt and clay contents amongst all those 61 soils and sediments. And so we can see that the extent of deviation for the short chain is much greater for the soil with the high silt and clay and lower for the one with the lower silt and clay. So most likely we have sorption controlled by additional mechanisms such as electrostatic interactions, particularly for the short chain. Okay, going back to that question of the KOC approach. Here are the data plotted for the long chain PFAS only for soils and sediments with organic carbon contents greater than 1%. So this represents a subset of all of the data shown prior. And we can see that the data pretty much are well represented by this log linear relationship. And I'd like to note here the benchmark, these dark red pluses. There's one here, there's one here, and there's one here. These benchmarks represent log KOC values determined for organic media, meaning human and peat, where we would anticipate that the sorption would be mediated by organic carbon constituents of those media. And so this is further evidence that perhaps the log KOC approach may be reasonable for the long chain PFAS for soils with larger organic carbon contents, but not for short chain PFAS. And finally, again, we need to note that these data represent only the standard PFCAs and PFSAs, and we need to investigate other PFAS types. Okay, moving on to surfactant behavior and absorption at the air-water interface. There are two primary ramifications of this accumulation at the air-water interface. One is the potential to cause surfactant-induced flow, and the second is increased retention and retardation for transport. So we'll focus on both of these. In terms of surfactant-induced flow, what does this mean? So here in the upper left figure, we have a standard data set for measurements of surface tension of PFAS as a function of the concentration in bulk solution. So we know that the surface tension is decreased as we increase the concentration of the surfactant, or in this case, PFAS. So moving over to the right, changes in surface tension impact the capillary pressure, as shown here in this equation. So as we have increases in concentrations of the surfactant or PFAS, this reduction in surface tension at some point may become sufficient that we reduce capillary pressures, and therefore we induce water flow. And so this is what we mean by surfactant-induced flow. So this surfactant-induced flow can lead to transient flow conditions, which can impact the transport of any solute present in solution. It also causes changes in the local water saturation, which then causes changes in the magnitude of air-water interfacial area, which then impacts the magnitude of retention of the surfactant or PFAS at the air-water interface. And so you can see that this can lead to complex interconnected flow and transport behavior. Now looking at fluid-fluid interfacial retention, here we have depictions of a pore sequence where we have PFAS present in solution in blue and at the air-water interface and at the solid water interface. We of course know that in the source zones, we can also have non-aqueous phase liquids such as chlorinated solvents or hydrocarbon fuels present. Excuse me. And we can also have association of PFAS with the NAPO phase, but we won't be focusing on that today. We'll be focusing on absorption at the air-water interface. So what is the impact of the presence of air and air-water interfaces in unsaturated media? So this can be shown with a set of laboratory experiments, miscible displacement, or colloquially referred to as column experiments. So in this figure here, we're plotting relative concentration on the y-axis, which represents the concentration of the constituent in the effluent of the column, divided by the input concentration. As a function of the x-axis, which is pore volumes, a non-dimensional time, this represents the volume discharge moving through that column divided by the retention volume in that retention water volume in that column. So to conduct these experiments, we take our soil or sand or porous medium of interest, pack it in the column, we saturate it with an electrolyte solution, then we start injecting our tracer solution, and then we monitor the effluent, collect effluent samples and analyze the concentrations. And so here we see the results of two sets of experiments. The first set we have under saturated conditions, and this is for PFOS. We see this, what we've referred to as the breakthrough curve, comes out very early at a very small number of pore volumes, indicating very low retention because the sorption of PFOS by this medium is very low, the solid phase sorption. Then we drain some of the water out of the column, create unsaturated conditions. Then we conduct the experiment again with everything else the same. And now we have the yellow and red circles representing the breakthrough curve of PFOS under these unsaturated flow conditions. And we can see that the breakthrough curve arrives much later, approximately 10 pore volumes, indicating much greater retardation. And this is due to retention at the air-water interfaces that are present in this unsaturated media. And retardation is a function of the PFAS molecular structure. In this case, here we're showing breakthrough curves for a non-reactive tracer that has no retention at the air-water interface or sorbed by the soil, versus Gen X, which has a retardation factor of 1.4, PFOA, which has a retardation factor of 2.3, and then PFOS, which has a retardation factor of 7 for this particular system. So we can see greater retardation for PFOS compared to PFOA versus Gen X. Again, due to adsorption at the air-water interface. So going back to our simplified retention analysis, we see again the retardation factor, and now we're focusing on this term on the far right-hand side, which represents the magnitude of the air-water interfacial adsorption. And so we have the Ki, which is the air-water interfacial adsorption coefficient, and we have Ai, the air-water interfacial area. So let's look at these two terms. So the air-water interfacial absorption coefficient is a function of PFAS molecular structure, as we mentioned. It's also a function of concentration, particularly at higher concentrations, and also a function of solution composition, such as the ionic strength. Now, we conducted a QSPR meta-analysis for PFAS absorption at the air-water interface, where we have compiled data for 61 individual PFAS of all structure types, and we've also included some hydrocarbon surfactants for comparison. So here is the result of the meta-analysis. So again, we have 61 different PFAS represented here. Each of these individual data points represents the log air-water interfacial absorption coefficient for that particular PFAS, plotted versus their molar volume. So the red squares represent standard PFCAs, the yellow represents the PFSAs. We also have branched PFCAs, we have polyanionic PFAS, we have cationic PFAS, zwitterionic PFAS, and non-ionic PFAS, as well as a couple of alcohols. And then the hydrocarbon surfactant comparisons are in the black circles. So we can see that all of these different types of PFAS with different molecular structures are all represented quite well by this single log linear relationship between the log, the air-water interfacial absorption coefficient, and the molar volume. So as we mentioned before, this log linear relationship is indicative that the hydrophobic interaction mechanism is mediating the partitioning, in this case, the adsorption or accumulation at the air-water interface. Now, how about the air-water interfacial area? So this is a function of the soil properties. So interfacial area is generally larger for media with smaller grains and larger solid surface areas. In addition, interfacial area increases non-linearly as a function of the water saturation. So as the air content increases, as we continue to drain a soil, for example, we have greater and greater air-water interfacial area. And so this figure represents the log linear functions fit to measure data. I'm not showing the measure data points, but just the log linear fits to 3 different media. So we have the soil, which is the smallest diameter and has the largest solid surface areas. The GSSA represents the geometric solid surface area, just as a function of the diameter, assuming smooth spherical grains. Then the NBSSA is the nitrogen BET solid surface area, which accounts for microscopic surface roughness. Then we have the sand, medium diameter sand here with medium GSSA and NBSSA. And then we have a larger diameter sand, 1.2 millimeters, way down here, represented by the dotted line. So again, we can see very significant differences in the magnitudes of air-water interfacial area between these 3 different media, and as well as a function of water saturation. So we have multiple questions for field scale applications with respect to adsorption at the air-water interface. First is surfactant-induced flow relevant? So based on our experiments, bench scale experiments, and modeling simulations, it appears to be unlikely to be significant for lower concentrations typically present at many sites. However, it may be relevant under high concentration conditions. Second, how do we determine the Ki, the air-water interfacial absorption coefficient? Well, based on the QSPR analysis, it appears that we are able to obtain representative estimates from that type of a modeling approach. How about determining the air-water interfacial area. So this is one of the most difficult parameters to characterize and quantify, particularly at the field scale. So we've developed prediction models based on different soil properties. However, they need testing for a wide range of soils. We've only tested them for a very narrow range of sandy soils. And so this is one of the most difficult components and elements to trying to characterize and simulate PFAS transport in the Vadose zone is the determination of air-water interfacial area. Okay, so as we can see, PFAS retention and transport in the Vadose zone is quite complex. So here's another opportunity for questions before we move on to the final section.
Yes, Mark, we've got a few questions here. Does the surfactant-induced flow effect suggest the increase in mobility of other co-contaminants?
It could, yes. So if we have significant surfactant-induced flow, then we have greater flow locally. And so any constituent that would be present in solution could be affected by that enhanced flow.
Okay. And then the other question we have is, could there be an accumulation of PFAS over time under the older basins?
Yes. So we're going to be coming up now to some field simulations and field measure data sets. So I think once we go through those materials, that will help answer that question. But yes, that's the hypothesis, that over the years, we've had accumulation of PFAS in the Vadose zone, particularly beneath the older basins. Is that it?
I believe that's it.
Okay. All right, then we'll move on to the final section where we will examine PFAS migration in the Vadose zone with different simulations and field data sets. So first, let's look at dynamic infiltration and recharge impacts, where we have simulated a 10-day precipitation event. So this is a single precipitation infiltration event, and we want to see what's happening with respect to water saturations, air-water interfacial areas, and how that influences PFAS retention. So these simulations were conducted with my colleague, Dr. Bo Guo, here at the U of A. So we have this 10-day precipitation event. We can see here on the left side figure, the wetting front propagating downward through the Vadose zone. So we have a 4-meter deep Vadose zone. Here is and the water saturation is on the x-axis. We can see this large increase in water saturation representing the infiltration of the water, right? So our wetting front, and then we see after 1 day, then 2 days, 5 days, and 10 days, that propagation downward. Now, as a result of these changes in water saturation, we see on the right-hand side figure that air-water interfacial area changes significantly. So specifically, as the water saturation is increasing with this wetting front, the air-water interfacial area decreases. And we see that change in air-water interfacial area propagating downward as well, following the infiltration front. So how do these changes impact PFAS retention? So in this series of plots, we have the pore water concentrations on the left-hand side and the total soil concentrations on the right-hand side. So pore water concentrations, of course, represent PFAS just in the pore water, the local pore water. The total soil concentration represents all PFAS present in the soil volume, which includes PFAS in the pore water, sorbed PFAS, and PFAS at the air-water interface. So going back to the pore water concentrations, we can see very minimal changes in the concentrations for PFPEA, a short chain PFAS. And this is because PFPEA, due to its shorter chain, has a relatively low interfacial activity. So it doesn't have significant absorption at the air-water interface. We can see greater changes for PFOA and the largest changes for PFOS. And the PFOS has the highest interfacial activity of the three. It has the greatest air-water interfacial absorption coefficient, for example. Now moving over to the total soil concentrations, we'll start at the bottom. We see almost no change in the soil concentrations for PFOS. So we see minimal leaching for PFOS because of its very high retention due to sorption, but primarily absorption at the air-water interface. We can see a small amount of change in the soil concentration representing leaching for PFOA, but we can see significant changes in the total soil concentration for PFPEA. So we have significant leaching occurring for PFPEA because of its comparatively low retention. So that was an illustration of what happens with a single infiltration event. Here are some simulations showing long-term PFAS migration in the Vadose zone. So these are simulations conducted for a model FTA site using properties of a local soil in Tucson for PFOS specifically. So we conducted a series of simulations for two climate types, arid over here on the left and humid here on the right. And we have the z-axis 5-meter Vadose zone plotted here and versus aqueous concentrations. And so each of these curves represents the aqueous concentration front for PFOS at different time periods. So the first thing we can see if we look at these transit times I've put here for 2 meters, the transit times are much shorter for the humid climate as we would expect based on the much higher recharge rates, right? So as we would anticipate, the magnitude of recharge is a critical factor influencing the mass discharge of PFAS to groundwater. Second, we can compare for each of these two sets of climates, the transit times for simulations conducted with no air-water interfacial absorption. So we just turn that off in the model versus when we include air-water interfacial absorption. So the transit times are much shorter in the absence of air-water interfacial absorption. So these numbers, comparing them, helps to illustrate the significant impact that air-water interfacial absorption can have on the retention of PFAS in the Vadose zone. But of course, as we mentioned before, that will be a function of the specific site conditions and the specific PFAS. So now we can look at long-term distributions of PFAS in the Vadose zone. So these are data from a field study of PFAS Vadose zone concentrations. So these data represent 124 boreholes across 30 different AFFF sites for which at least 8 depth discrete samples, soil samples, were collected for each borehole. And so the depth interval here shown on the vertical axis in a normalized rank represents from the ground surface here, 1, to the top of the saturated, down here, 8. So each of the different sites may have a different specific depth to groundwater, but we have at least 8 depth discrete samples collected from each borehole for the data included here, and they're ranked by their relative depth. So looking at the bar chart, we can see, first of all, that the magnitude of total PFAS concentration declines exponentially with depth. Second, we can see that the proportion of long-chain PFAS, represented by blue, is much greater in the shallower intervals, whereas the short chain comprise the largest fractions for the deepest intervals. So these results in total provide evidence of both downward migration of PFAS as well as chromatographic separation. So finally, we can look at measurements of soil versus pore water concentration distributions for actual field samples. So these data represent a compilation of 3 separate studies noted in the legend, where samples of soil were collected and PFAS concentrations were measured both for the soil and specifically for pore water. So when we look at comparing soil versus pore water concentrations of PFAS, here we defined CS and CPW. The ratio of the total soil concentration to the pore water concentration is a function of this RD, which we can see here is the same as our retardation factor that we've discussed previously. So based on this retardation factor that we have discussed, we can see that for larger KDs and larger KAWs, the air, water, interfacial absorption coefficient, that we would anticipate to have larger R values and therefore larger ratios. So we know that longer chain PFAS, as we've seen from the prior QSPR analyses, both have larger KD values in general and larger air, water, and facial absorption coefficients. So based on that, then we can examine the actual measured ratios of soil concentration to pore water concentrations as a function of the molar volume. And we can see for all 3 studies that the measured data sets fall nicely along this log linear relationship. And so at least for these 3 studies, there's evidence that the PFAS is distributing between soil and pore water as we would anticipate based on our understanding of solid phase sorption and air, water, and facial absorption of these PFAS. So I focused primarily on retention processes and how they influence migration of PFAS in the Vadose zone, but of course there's many other factors that can be relevant for sites, including physical heterogeneity and preferential flow, which may reduce retention, geochemical heterogeneity, of course, the presence of PFAS mixtures, the presence of co-contaminants, and finally, precursors and non-characterized PFAS. So all of these are very important and are under investigation by our group and other groups as well. So in summary, the retention and leaching of PFAS in the Vadose zone is complex and influenced by multiple processes. Adsorption at the air-water interface can be very significant depending on the PFAS and site conditions. Determining air-water interfacial areas at the field scale is difficult. Solid phase sorption can be complex, and we need to be aware of the KOC approach that may not be representative for many PFAS. And finally, models are being developed by us and other groups to simulate PFAS transport with applications for quantifying leaching and mass discharge to groundwater, determining soil screening levels, and evaluating mitigation and remediation actions. So thank you very much.
Great. Thank you, Mark. We've got a few questions over here. First off is, which software are you using for modeling?
So we, in collaboration with my colleague I mentioned, Dr. Bo Guo, we've developed a suite of models, and so they range from a bespoke 3D complex model that has all the processes that we can think of that are important, to ranging to a hydrous-based simplified model, to a analytical solution-based model that's implemented in different platforms, including Excel. And then we've actually also recently modified the standard EPA dilution attenuation factor model that's used for determining soil screening levels, the 1996 model. So we have revised that, and that, of course, can be done on paper and pencil or in Excel.
Thank you, Mark. We have another question regarding the type of PFAS typically found in wastewater effluent. Are they cationic, anionic, zwitterionic, and is it more short chain or long chain?
I'm going to jump way back to the case study to answer that. And of course, these data are only for this particular facility. At the time of our study, Tucson Water was analyzing for the first 16 PFAS, and these are the 8 for which there were concentrations present. So there were the other 8 PFAS that were not determined to be present, at least above detection limits. But again, they were analyzing at the time only for the first 16. So I'm not sure now if they've expanded that suite of PFAS. But you can see here at the bottom, the ones that were determined to be present from these initial characterizations are the common anionic PFAS, right, that we are typically dealing with. So that's the most information I have for this site.
Thank you, Mark. On that, I guess my question is with the original basins versus the newest basins in the groundwater sampling, are you seeing the effect that partitioning and in the upper columns? I mean, in the upper sections of the Vadose?
Yes, so looking at this map, we see that there are PFAS present, and we can see here in the bar chart that there are low levels of PFAS in groundwater beneath that newest basin. And they're very, very similar to the concentrations that are present in the currently present in the treatment plant effluent that's coming into the recharge basin. So they are present, but at comparatively quite low concentrations. And because of the operation status of the facility, we would expect there would be relatively rapid transport of PFAS from the basin to groundwater because of the ponded conditions, very high infiltration recharge rates. So we do see them present. One of the major uncertainties for this facility, for our study, is what are the distributions of PFAS in the Vadose zone. And so that has not yet been measured, but we are currently planning to conduct some additional work at the site where we hope to measure PFAS concentrations in the Vadose zone before, during, and after a recharge event. So hopefully, once we can do that, that will provide some further insight into the PFAS dynamics in the Vadose zone at the facility.
Right, and we've received some additional questions. Do you think soil redox, or do you think redox changes in the soil have an impact?
There is potential for change in redox as we have the fluctuating groundwater levels. So we could have changes occurring right at that capillary fringe groundwater interface. And for example, we saw from some of the sorption data sets that in particular, the short chain PFAS their sorption may be influenced significantly by electrostatic interactions with other constituents of the soil, such as metal oxides. And so changes in redox could influence some of these soil constituents, which could then perhaps influence the sorption of the PFAS. So I could see there could be some potential.
Okay, well, the questions are rolling in. We have one. MP3D USGS allows for simulation absorption in the unsaturated zone. MEF6 currently does not, unfortunately. Do you have an opinion as to whether MP3D USGS would be an appropriate tool for simulating air-water interface sorption?
So there are a number of ways in which you can attempt to incorporate the impact of air-water interfacial absorption on transport. So answering the prior question about the modeling platforms we're using, in the complex model, we have full descriptions of the air-water interfacial absorption process. So as a function of concentration, for example, as a function of time, allowing it to be rate limited. However, in simplified models, you can use this type of retardation factor approach, and it can produce representative results under certain conditions when, again, for example, the air-water interfacial absorption can be assumed to be linear, can be assumed to be under equilibrium conditions, not influenced by other co-constituents, other PFAS present, right? So under a long set of conditions, this type of simplified approach could be used, and then you could modify the retardation factor in that platform or other platforms to include these additional terms here on the right. And so that would give you an additional greater retention through this retardation factor. So that is possible, but again, we have to be cognizant that its representativeness would be predicated on a set of conditions.
Okay. Thank you, Mark. And another question, in the bar chart showing the chromatographic separation, looks like the amount of the short chain PFAS don't change significantly with depth. Does that indicate that the short chain PFAS is more mobile?
Here we go. Yes, so we saw from some of the prior work, right, that the short chain PFAS have comparatively lower magnitudes of solid phase sorption, as well as lower magnitudes of air-water interfacial absorption. So those two in combination would be primary sources of retention in the Vadose zone. And because they are comparatively much smaller impacts for the shorter chain, most of the shorter chain, then we would expect the shorter chain to have much less retention, much less retardation, and therefore to migrate comparatively much faster compared to the longer chain PFAS. And that's what appears to be represented by, as was pointed out in this figure and in other types of plots of vertical distributions of PFAS from other field sites, as well as our modeling simulations.
Thank you, Mark. I Another question, does PFAS sorbed at the air-water interface get transported deeper in the Vadose zone with subsequent wetting fronts? Is it still in the aqueous phase at the interface, or does it volatilize into air phase where it might be transported via air phase flow?
So yeah, that's a very interesting question, and it depends on the specific PFAS. So for our standard PFAS, such as PFOS and PFOA, they have very, very low vapor pressures. So we would anticipate minimal concentrations in the soil atmosphere or the vapor phase. So their distributions would be a function of retention at the soil water interface and air water interfaces, as we've been discussing and shown here. And their rates of migration, again, can be a function or is a function of their chain length or their size. So we can have significant migration even in a single event for some short chains such as PFPEA here. Now, going back to the question of the presence in the vapor phase, we do know that some PFAS, particularly some of the precursors, have significantly high vapor pressures, and their Henry coefficients are similar to some of our standard VOCs of concern. And so that's a newer area of research for PFAS, and some of our preliminary work has shown that for these PFAS with high vapor pressures, that there can be facilitated or enhanced transport in the vapor phase through gas phase diffusion. We know that gas phase diffusion coefficients are roughly 4 orders of magnitude greater than aqueous phase diffusion coefficients. So vapor phase migration can be significant for these volatile PFAS, which again is a newer research area.
So as a question, would you expect PFAS to transport more quickly in a completely saturated system, or a system like a modified aquifer recharge system where you have increased, you've got a larger Vadose zone and you're basically flushing it down frequently?
Yes, so the rate of migration for PFAS that are significantly absorbed at the air-water interface, their rate of migration will be significantly influenced by the magnitude of water saturation, which controls the magnitude of the air-water interfacial area present. So for systems that are, for which we have saturated flow conditions for long periods of time versus systems where we have lower water saturations for most of the time, we would anticipate much greater, much more rapid migration for the fully water saturated conditions, yes. But for PFAS that have minimal absorption at the air-water interface, then those changes in water saturation and air-water interfacial area will not have a significant impact on their rates of migration. So it really depends, again, on the PFAS.
Thank you, Mark. And that is all of our submitted questions at this time.
Okay, well, thank you very much.
Again, a recording of this presentation and slides will be present at gwpc.org, the ASR MAR work groups subsite. Thank you very much, Mark.
Thank you. Goodbye, everyone.